Welcome back, scholars. Today we'll start a three-part series where we will look at all things relating to rational functions, expressions, and equations. We'll begin by looking at rational functions. Let's get started. We'll start by defining a rational function. In general, we're looking at a function which consists of a ratio of two polynomial functions. Remember that a ratio is another way of describing or defining a fraction. So, in the numerator, we have some polynomial, we'll call it p of x, and in the denominator, we have another polynomial function, we'll call it q of x. Now, this definition only holds up if the polynomials p of x and q of x are not the constant expression 0. And, real quickly, remember that when we say polynomial, we're talking about an algebraic expression which consists of variable and constant terms. The variable terms can and often do include exponents, but those powers can be positive integers only, so no negative exponents and no rational exponents, which also means no radicals. We'll start by looking at the simplest rational function, which is called the reciprocal function, and it is in fact the reciprocal of the parent linear function y equals x. In this case, our numerator polynomial is the constant 1, and the denominator consists of the first degree linear polynomial x. On the right, we can see a picture of the function, and right away you should notice that it's nothing like the polynomial functions it's built from. We can see that the function itself is discontinuous or appears in two branches, so to speak. Next, we can see that there are these areas where the function very clearly does not reside. For example, the function is not defined at all for the input x equals 0, and the function does not produce an output at y equals 0. If we look at the construction of the expression 1 over x, we can justify each of these features. First, we can't divide by 0, so this explains why we have a discontinuity as we approach x equals 0. Similarly, since the numerator is the constant value 1, no matter what we divide by, we'll never get 0. Think of it like tearing one piece of paper maybe hundreds or thousands of times. We'll end up with a very small piece of paper, but we can't divide something into nothing, so 0 is not a possible output. Now, with rational functions, we can of course describe end behavior. That is, what happens to the function as x gets very large or as x gets very small. Be careful not to answer these questions in autopilot. This function does not approach infinity as x gets large or small as it does with the linear or polynomial functions. Instead, it approaches that horizontal asymptote at y equals 0 on both the left and the right-hand sides. In addition to end behavior, we can also describe the behavior of rational functions as they approach certain constant values. For example, for f of x here, which is pictured, we can see that there is a discontinuity where x equals -2. We can see that as the inputs get closer and closer to -2 from the left-hand side, the function veers towards -infinity. On the other side, as x gets closer and closer to -2 from the right-hand side, the function instead veers towards positive infinity. This concept of approaching a vertical asymptote from the left or right-hand side is represented using limit notation. Under the lowercase letters lim, which is shorthand for limit, we denote the constant value that x approaches. The superscript plus or minus tells us whether we are approaching that constant value from the right-hand side, the positive side of the number line, or from the left-hand side, the negative side of the number line. We use equation form here and read this out loud as the limit of f of x as x approaches -2 from the right-hand side equals infinity. Or, for the left-hand side, the limit of f of x as x approaches -2 from the left equals -infinity. To find the domain of a rational function, we seek all the values that would lead to a denominator of 0. It's a good idea to keep the fundamental theorem of algebra in mind here and the degree of the polynomial in the denominator. For example, a linear function will have exactly one root, while a second-degree polynomial, a quadratic, will have 2 roots. Not all roots are real numbers, but you should stay in the habit of accounting for all the roots so that you don't inadvertently miss a value that should be excluded from the domain. Here are a few examples for you to browse through if needed. You'll often find it easiest to factor second and third degree polynomials to find the zeros. Once you're comfortable finding the domain restrictions, we can go a step further by classifying those excluded values as discontinuities. Rational functions will have up to 2 types of discontinuities: holes, which are also called removable discontinuities, and vertical asymptotes, which are called non-removable discontinuities. Holes occur when a factor, such as x minus b, is present in both the numerator and the denominator. When written in lowest terms, this factor is often simplified out, hence the name removable. These are the easiest to forget because oftentimes students will simply cancel out common factors and completely forget that value is still excluded from the domain. Vertical asymptotes appear wherever there are factors such as x minus a present only in the denominator and not also in the numerator. Let's look at a few. On the left-hand side, we have a rational function consisting of 2 quadratic polynomials. Go ahead and write f of x in fully factored form. We have two unique factors in the denominator, and they are not also present in the numerator, so this rational function is already in lowest terms. We classify these discontinuities as vertical asymptotes, so x equals 2 and x equals negative 2 are both restricted from the domain, and they are both vertical asymptotes. On the right, we have a rational function with a quadratic numerator and a cubic denominator. Again, write g of x in fully factored form. In the denominator, since it's a third-degree polynomial, I'm expecting up to 3 excluded values. I have x equals 0, which is not a factor of the numerator, so I classify this as a vertical asymptote. I have x equals negative 3, again, not present in the numerator, so another vertical asymptote. And finally, x equals negative 2, which is present in the numerator as well. Assuming that x is not equal to negative 2, I could reduce this rational expression down to lowest terms. So this would be considered a removable discontinuity, also known as a hole. Overall, there are 3 excluded values from the domain of this function. That wraps up our first look at rational functions. Next time, we'll look at graphing, and later on, we'll review solving rational equations. See you next time.